Hello and welcome back to Retured. I'm Dr. Amita Kapoor. Today we are surrounded by the marvels of large language models. They can write poetry, debug code, plan our vacations. But these powerful models have a profound hidden secret, a flaw that is baked into their very design. They can't learn, not in the way you and I do. Once their training is complete, they're essentially frozen in time. Their knowledge is static. Think of it this way. A powerful LLM is like a person with a severe case of anterograde amnesia. This is a real neurological condition where a person can't form new long-term memories after an injury. They remember everything from their past, their training data. They can manage the immediate present, the data in their context window, but ask them what you talked about 10 prompts ago. They have no idea. Nothing new ever gets saved to long-term memory. This is one of the biggest challenges in all of the artificial intelligence. How do we build models that can continually learn from new experiences just like we do? Well, a brilliant new paper from researchers at Google suggests we have been looking at the problem all wrong. The paper is titled Nested Learning, the Illusions of Deep Learning Architectures. Today, we are going to break this paper down. We will use simple analogies, and by the end, you will understand why the very idea of deep learning might be, in a sense, a beautiful illusion. And this topic is incredibly close to my heart. My work, both as an educator at places like Oxford and through Retured, sits at this exact intersection of AI, cognitive science, and neuroscience. This paper connects the dot in a way I find truly fascinating. So, why don't our brains suffer from this amnesia? Our brains are plastic. They are constantly reorganizing themselves in response to new experiences. This is called neuroplasticity. The paper highlights that human memory is a process of two-step process. First, there is a rapid online consolidation that happens almost immediately. Then there is a slower offline consolidation, like when you sleep, that reorganizes those memories for the long term. Our current large language models are missing that first online step. They have no mechanism to immediately start saving new information. But there is a second, even more profound secret. The brain does not have a single centralized clock, like a CPU in a computer. Instead, it operates on multiple timescales at once, which we can see as brainwaves. Think of it like a company. You have frontline workers, like your sensors, operating at a high frequency, reacting every second. And you have a CEO, like your planning functions, operating at a low frequency, making one big decision per quarter. The brain does this. The paper notes that earlier layers, like sensory input, update quickly, while later, more integrative layers update slowly, over longer cycles. It is an incredibly efficient system. Our AI models, with their single, rigid clock step, are completely different. Okay, so brains have neuroplasticity and multi-scale clocks. LLMs are static and have one clock. Now here is where the paper drops its first bombshell. It says that our deep learning models are not really deep, not in the way that matters. When we see a diagram of a deep neural network, we see this, a stack of layers. This is the standard deep learning representation. It shows the architecture, the training process, with its optimizer is shown as a separate thing, an arrow pointed at the model. The authors call this a flattened image of what is really happening. They propose a new representation, nested learning. In this view, the model is not a flat chain. It is a nested set of optimization problems. Each component is its own learning module with its own objective and its own context flow. And crucially, these modules are organized by their update frequency. This might seem abstract, so let us break it down to the simplest example imaginable. Let us talk about gradient descent. What is gradient descent? It is the algorithm that trains most neural networks. The analogy is simple. You are on a foggy hill and you want to get to the bottom. You feel the slope at your feet, that is the gradient, and you take a small step in the steepest downhill direction. You repeat until you are at the bottom. The update rule is just weight at time t plus 1 is equal to weight at time t minus the learning rate eta into the gradient of the loss function. From the nested learning perspective, this simple process is already a one-level optimization problem. Now the paper reframes this. It is an associative memory. Stay with me. The model, the weights, is learning to associate an input x with a local surprise signal. That is just a fancy name for the gradient. It is learning to map what I saw to how wrong I was. Now let us add momentum. Instead of just a person stepping, you are now a heavy ball running down the hill. You don't just move based on the current slope. You have the momentum from the past steps. This helps you roll over small bumps and get to the bottom faster. The update rule gets split into two. First, you update your momentum. Momentum is equal to beta times momentum minus the gradient. Then you update your weights, where weight is equal to weight plus momentum. And here is the aha moment. In the old flat view, this is just a fancier optimizer. In the nested learning view, this is now a two-level system. The weight update is the slower outer loop, that is level 1. The momentum update is the fast inner loop, that is level 2. The momentum term M is itself an associative memory. It is its own little optimization problem whose job is to compress the past gradients. The optimizer is not separate from the model. It is a nested two-level learning module. This one simple example unlocks the whole paper. If gradient descent with momentum is a two-level system, what about our other more complex tools? What about the transformer? The paper argues that a transformer is also a two-level system, just like the gradient descent with momentum. Level 2, the fast loop, this is the attention mechanism. Think about it. The attention matrix M updates on every single token. It is an inner loop that is constantly running, figuring out which tokens to pay attention to. This is a fast weight system. Level 1, the slow loop, this is the feed-forward network, the part with the big, heavy, multi-layered perceptron layers. And now we have found the source of amnesia. When does the slow loop, the fast-forward network, the long-term memory get updated? Only during pre-training. After the model is deployed, the fast-forward network is frozen. Its update frequency is 0. So you have this fast attention system that is frantically processing new information, but it has no way to save its conclusion to the slow, long-term memory, because that part is read-only. That is the amnesia. The connection between the fast and slow levels is broken after training. This nested learning framework does not just give us a new description, it gives us a prescription. It tells us how to fix this amnesia. If the problem is the giant gap between the fast loop, attention layers, and the frozen loop feed-forward network, the solution is to add intermediate levels. We need to build a continuum of memory, just like the brain's different wave frequencies. This is exactly what the authors built. They call their new model HELP, which is a combination of other cool ideas like the self-modifying Titan and the continuum memory system. Let us look at the HOP architecture as seen through the nested learning lens. It is beautiful. Unlike the transformer's two flat levels, HOP is a true hierarchy of update frequencies. At the bottom, you have the self-modifying Titan, the attention-like part. It updates at the highest frequency on every new token. This is your immediate present or working memory. Above that, you have a higher frequency feed-forward network. This feed-forward network is not frozen. It updates, for example, every 16 tokens. It is consolidating the work of the fastest layer. Above that, a mid-frequency fast-forward network. It updates say every 1000 tokens, it consolidates the level 3 memories. And finally, a low frequency fast forward network. This is the true long-term memory, updating maybe every 10 lakh tokens. This is the brain multi-scale clock. It is the CEO and the frontline workers all connected. Now, when new knowledge is learned by the fast layer, it does not fade away. It gets passed up to the level 3 and consolidated. Then that consolidated insight gets passed to level 2 and so on until the most important persistent knowledge makes its way to the long-term memory at level 1. It is a cascade of memory consolidation. It is online learning, the very thing large language models were missing. And the result? The paper shows that this HOPE model, built on nested learning principles, perform exceptionally well, often outperforming standard transformers and other modern architectures on a range of language modeling and reasoning tasks. So let us zoom out. What does this all mean? The paper suggests that deep learning might be a misnomer. We have been building models that are spatially deep, many layers, but temporally flat, only 1 or 2 update frequencies. This flatness is the source of their core limitation, the inability to learn continually. The nested learning paradigm gives us a new lens. It tells us to stop thinking about just the architecture and to start thinking about the nested dynamics of the learning process itself. The real depth isn't in the layers, it is in the hierarchy of update frequencies. And this is where, in our own work at Retured, I see the most potential. By combining these ideas from computational neuroscience like multiscale updates, neuroplasticity, and memory consolidation, with our AI architectures, we can move beyond creating static amnesiacs. We can start to build models that are truly alive, models that learn from every interaction, that adapt to a changing world, and that, like us, build a lifetime of knowledge, one nested level at a time. This paper does not just give us a new model in hope, it gives us a new hope for the future of AI, a future that is not just deep but truly nested. Thank you for joining me on this deep dive. I'm Dr. Amita Kapoor for Retured. If you found this breakdown helpful, please subscribe. And I have a question for you. What other illusions do you think we hold about AI? Let me know in the comments below.